and start recording. Okay.
Okay, good. So last time, if you look at the lecture slides, I changed the title, but we started looking at search-based methods for motion planning, right? And we looked at the Dr. Eureka just as an example of a search domain that we want to start out with. And we want to learn a little bit about search itself. Now, we ended up implementing a search algorithm last time. For this game. We already implemented that on our computer. And we mentioned that exponential complexity is our enemy. Because it grows extremely quickly. Now here, in order to implement the search algorithm, you need to consider the following questions. First, how do we represent the search space that we're searching through? Usually, that refers to what is a state if we are actually searching in the state space. Sometimes we're using the plan space that we search through, and I'll give an example of that later on. That often leads to more powerful methods, or sometimes it can lead to more powerful, more faster planning methods, problem-solving methods. Then we need to have a function that tells us whether we reached the goal state or not. We need a function to generate the children given the current state of the search. And then we'll discuss heuristic functions and cost functions later on. So we decided to use the following state representation where the stacks of the three tubes are represented by strings which correspond to red, green, and blue balls. And the leftmost one is always the bottom ball in the tube. And then here's our generate children function. And then we can generate the number of children from particular states. A goal state that says we want to return to blue, 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 green, green, red, red. And then the search algorithm. Which, given this initial state, then we should be able to find the solution. And in this case, it simply returns that the solution was found. Now, given this function, you can try yourself. And Here we print out the current list of states. So first thing that we have so far is the routine, our search routine only returns whether there is a solution or not, right? But it doesn't actually tell us how to get to that solution. So modify this code, copy those pieces of code, and then modify it so that it will actually return the solution path. So it should tell you pour 2 balls from tube 1 into tube 3. Pour 1 ball from tube 3 into tube 2, that sort of thing. And then print that out instead of just found or not found. So first thing you want to do is add the solution path to the output. Second, we want to find out how many different states are there, or let's fix it. Fix the reversal operator. There's a problem with the reversal operator if you think about it. The way that it's implemented at the moment, the one where I take a tube and just pull it upside down, right? So you should figure out how to fix that so right now it will generate illegal solutions. So figure out why it does that and then fix it. And then 3, we want to know how many different states there are. And then we want to find the maximum solution length. So what's the most difficult problem to solve for the Dr. Eureka game? Given any potential initial state and any potential terminating state. And don't run away, you're supposed to program. Yeah.
So these 4 are we have to.
Yep. Mm-hmm. Yeah. I just want to give you a chance to practice your programming skills. And I need to copy some. So we'll have to copy those three functions and then search unique is goal and successors. We need is goal, successors, and the search function. And then other than that, all you really need is the standard Python language. So you can use Code, Visual Studio Code, or any other editor to write your program. And here, as you see, if it's a goal state, I just returned that we found a solution, but I didn't say what the solution is. So now we want to fix it so that we actually find the solution. So first you can copy the code and run it, and then make sure it works, and then add your solution path. So yeah, that seems to run at least.
Just how the app should be added once we found the goal.
No. Once you found the goal, I think it'll be hard to add the path. Because for one thing, there may be multiple paths to reach that. Right? It's easier to construct the path while you're doing the search. then I can try a couple of things, but you try and find your own solution. In fact, the first one requires a little bit of additional structure, so think about that. So the first thing I would do is modify the code so that I can actually get an action, right? I want to specify what it actually did, so I converted it to a string with the various different actions that we can do. So one action is pour 1 from tube 0 into tube 1, pour 2 from tube 0 into 1, pour 1 from tube 0 into 2, so on and so forth. And that's going to be quite useful. And then we also have the flip actions. So I can flip tube 0, flip tube 1, or flip tube 2. Twist them over. Now, the string representation is nice, but that makes it difficult to, in the search algorithm, I don't actually need the numbers, so I think I'll just leave it like that. Yeah.
I'm afraid that when I reverse one to in the state, I will modify the original value of the previous state, because in Python there is not copy the value of the state, but
Yeah, but you can call .copy before you call flipping or anything, which is what I think my successor function does. Right? Here we copy the state. Now, state is an array of strings. Strings are immutable, so there's no point to, you don't need to copy the strings because you're unable to change them anyway. So this will copy the array of strings. So that's fine. And you say I forgot that in the, no, here too. The flipping also has a state copy first. So I think that's correct. But yes, you do need to pay attention to the semantics of argument passing in Python. If it's a list and you modify it, this will change everywhere else where that list is referenced.
Mm, mm. Here we're printing the key.
So this will be my solution to number 2. Sorry, this will be my solution to number 1. In order to be able to deal with the printing out the solution, you need to have 2 things. One, you need to generate actually an action name, like pour something from something into something else, or flip action, something like that. And secondly, and most importantly, you need to keep track of these actions. Now, that means I extended the queue, and you can see actually the change from the code that I had previously is very minor. There's just a couple of things that I have to fix. For one thing, in the queue now, I don't have just the state anymore, which is what we had before, but the 2 empty lists. The first one corresponds to the history of states that we went through to get to this node. And the second one is a list of actions that get me to that node. Right? Now, the states, strictly speaking, I don't need that at this point, but it'll come in usefully. It'll be useful later on, because when I now call generate children, then I get not just the set of children, but each child now consists of 2 parts. One is the new state, and the other one is the action that generated that state. And now what I do here is, what does this line actually do? That is a little bit of Python magic, but it's pretty handy to know. Actually, I don't need to write it that complicated. So here, initially, what I had assumed was that the state is equal to, that the history incorporates the state and the action, but then actually history and state are split over 2 separate lists. So let's keep it that way, then the code is easier here too. Then I just have to say if child state not in the history. And then that's much easier to understand. And yeah, so because that's why I split them up into two lists, but then I forgot that I'd actually done that. So here we're simply checking if the new state that is generated, if we already went through that state before, in which case it doesn't make sense to expand that node any further. It'll save us work later on. In breadth first search, it's actually not super important, but when we look at depth first search, it's crucial that you include that step to avoid infinite loops in your plan. Right? Because this would trigger if I pour one ball from 1 into 2 and then I pour another one ball from 2 into 1, I'm exactly in the same state that I started out with. So that doesn't help me anything, right? So I want to avoid expanding that node any further. So if I already was in exactly the same state, if that state is already in my history, then I skip it. Only if it's not in my history, then I insert it into the queue. What I insert into the queue is the history plus that new state that I just added, and the current actions that got me there, plus the new child action. So then I have everything. When I pop the node from the queue, now I break it down into state, history, and actions, because now there are 3 components to a state. And then if I want to return the solution, instead of none, I zip the actions in the history, which simply matches them up. State 0, action 0, state 1, action 1, state 2, action 2, like a zipper. Zips them together. And then I have to reverse them, because the last thing that's in my, actually, where do I add them? I add them at the end, right?
Yeah.
Yeah, so in this case, I don't actually need to reverse them. State action, yeah. So they're actually already done correctly. Usually when I do this, I implement a recursive function, then they would be reversed. So now I zip up the actions in the history. And that just didn't come to light because the plan here is only one step long. So now let's take something a little bit more difficult and see if that works. So let's say we have BG, move one of the green ones from there to there. And then it didn't find the solution, so that's wrong position. I can't find a solution because one blue one is missing. So let's put the blue one in. Now I have 2 blue, right? 2 green and 2 red. So I set up a node limit, only 20 nodes, so that's not enough to find the solution. So let's go to 2000. initial. And wait, it prints too many. Because the queue, because of the exponential complexity, the queue can be quite big. If you want to print it, you want to make sure that you have a very short path only. The session crashed. We used up all available RAM because we were printing too much. Yeah, because it. So that would be a solution to the first problem. Now, figure out what's wrong with the reversal operator, the flip operator, and find a way in which you can fix that. Here's our search function. And now I want to get rid of this first. So just load that. Maybe the reference data expanded too many nodes. Okay, give it 20,000. And I just have to go to the washroom quickly, and I'll be back.
顺序应该是对的。第一排是原本，第一排上原本如果完全没有给它扣的，第一排会走出来，只是它这边头是它的直接条件走，然后把它可以放在直接放在那个光学面在里面。应该是。
Okay, so here's the solution now that it found for that particular problem. This also shows the problem that we have with the flip operator. So luckily I picked that one. If you look at this plan here, then it's starting with BG, GR, and BR. Right? So now we take one from tube 1, which is the green one, put it into tube 2. So we get B, GG, Y, tube 1 into tube 2. BG. Yeah. BGGR 1 into 2, so that red goes into here, right? So I get BRR, so that's correct. Then pour 1 from tube 0 into tube 1, so 1 here, the G gives me GG here, green, good game. And then flip tube 2, so tube 2 instead of BRR now is RRB, right? And then I pour 1 from tube 2, the blue one, and pour it into tube 0. But that last step is illegal, right? And it wouldn't work because when I flip the tube, I cannot take any balls out at the top. So fix your search routine so that particular mistake it's not going to make that particular mistake. Like this would be an illegal path now, right? In that case, we would classify our planner as being incorrect. It doesn't have the correctness property because it returns a plan, but that plan doesn't actually work in reality. Once you flip a tube, you cannot take stuff out from the top anymore because the tube is flipped. So then you can think about how to fix that in your program.
Should we increase the state count number we insert and state into because here we state that node plus 1.
Yeah.
It's not count. But it's not equal configuration combined here so that we add a new state.
Yeah, I think it does somewhere because yeah. So I just count how many nodes are actually pop up you.
So if we maybe it would not.
It doesn't actually trigger on the number of nodes generated. That's correct. But the point, in this case, it's okay because I don't really care about the, so what's possible is that it generates, if my limit is 200, it may generate 300 nodes, right? Because they're all in the queue, but it only pops off 200 and then it'll stop, right? I'm okay with that right now because this is just used as a simple limit to be able to stop the algorithm from running forever or too long. So just on the Google Colaboratory, I can sort of control how much runtime it's going to use. If you need to be absolutely precise, like if you want to control the amount of memory that is used, and each node contains exactly 50 bytes, then of course the memory used in the queue would be used as your stopping criteria, or something else. But in this case, the queue nodes also include different length data, so that doesn't really apply. So I think it's fine to just take the nodes popped off. But it's not, strictly speaking, it's not the number of nodes that we generated, it's the number of nodes that we actually visited. Yeah. But again, that number is not crucial. It's just so that it stops at some point, not goes forever. Yeah.
So the question is about how many states. So this is
No, it's how many different states are in the puzzle completely.
For the video, in your function here, like in the current, in a certain space, we just check the last two, and to see the last two, we can use the last two to generate the children.
No, we put all the possible candidates that can lead to a solution into a queue, and then I take them one at a time. I take them out. If I only have two tubes, right, so I don't have to draw so much, then I have B, B, R, R, right?
Yeah.
Then I can generate some children, right? So I can take one from here to there. So it would give me B, B, R, R, right? Or I can take two, which gives me empty B, B, R, R, right?
Yeah.
Or I can go the other way, R into there, so that gives me R, B, B, R, or R, R, B, B. So these are all the children that I can generate, right? Now from here, let's say one of these may lead to a solution, right? So after I process this one, now I need to process each one of those. So I put them in a queue, and then I take one of them out, one after another. Right? That's what the queue does. That's what the queue is for.
Flattened version of the.
It's not a flattening, it's keeping track of the leaf nodes.
Yeah, I mean, there's another recursively.
Correct, yes. But I'll show you in a second why I don't implement the recursive solution. Possibly, that's one issue. More importantly is by implementing it as a queue, it it's trivial to switch from depth first search to breadth first search or breadth first search to depth first search. The what?
Just by switching the to the queue, we can switch between DFS and
Correct, yes. So you can check the code and see how I can fix that, how I can switch that. So the queue the queue holds all the possible candidates that may lead to a solution that I haven't explored yet. that works in Python, maybe not. Oh, that works. So here, fixing the flip operator is many different ways you can do that. Basically, we have to remember whether the tube is open or flipped, right? So somehow we need to represent that piece of information in the state. And the way that I did it is I simply, in order to also show it graphically, I simply added the vertical bar at the end of the tube. So this means that tube is flipped around here, right? And here that tube is flipped around. So the top looks like the top is now blocked off. And similarly for this one here. And then I simply need to modify my code for generating the children. So now I check if the last element, if I want to move from T from into T2, I check if the last element from T from is not this character. If it is, then the tube is flipped, right? If the last character is this, that means the tube is flipped, so I can't pour anything out of it. So this has to be not equal to this thing. And this is not quite correct. And then for the T2 tube, I also check the same thing to make sure that T2 is not flipped. Because I cannot take balls out and I cannot put balls in. But that code is, there's some problem with it. Then here the pouring all works. And for the operators that flip it, I simply check. If the tube is flipped already, then I want to unflip it, right? So I need to take care, I need to reverse this one here. I need to take that out. So those two parts of the code are actually probably not what I want. I want the state is plus 1 plus that. If the state is flipped, then I cut it out, flip the thing and then add the if it's flipped, then it's state t from dot to -1 to -1. So it's reversing the tube in this case, and I don't copy the. This should be S. So if it's already flipped, then we take the flip symbol off, reverse it, and then it's not flipped anymore. And otherwise, we reverse it and add the flip marker. And then I can check that. If I add a flip marker here, flip to. Yeah, that's okay. This doesn't work correctly. I don't know why. I had the same problem last time. So length of state t -1 -1. This is unchanged, but this reversal here doesn't work. So it looks like Doesn't work for strings. Okay. So here, if we have BB reversed, then I flip it, then I get BB not reversed anymore. And the other one's GBR. So that's okay. The only problem now is in that particular code here, I check for -1, but the string may be empty, right? If the tube is empty. So I have to also check to make sure that the length of state T from is greater than 0. And the state, or if the length is equal to 0 or is not equal to the flip marker, then I continue processing this. If T from not equal to T2, and this gets more complicated then, and length of state T2 is equal to 0, which means it's an empty tube. And if it's a reversed empty tube, it would be just the bar, and that should be okay. Or this. And probably it would be nicer to code it like, instead of having this complex conditional, I just make it two conditions. So we have that, and now let's add an empty tube to our string index out of range. Now I want to flip the empty tube, so I need to check that as well. If length of state T is equal to 0, or then here we can flip tube 0, flip tube 1, and flip tube 2. But flip tube 2 doesn't work because this is reversed. And then if length of state t not equal to 0, and then if it's equal to 0, reverse it and add a thing to it, maybe 0, and other than that. So here now I can flip till 2, but it's empty, so it's only the top marker that will be set. So that should fix all our issues there. So now let's see if it finds a valid solution. Let's see if I have codes. Here I just need to copy that into Visual Studio Code to run it a bit faster on the local machine. think if you use the Google Collaboratory too long, it is not happy and puts you on a really slow compute infrastructure. Let's just see what this does. Desktop file on the desktop. User. That's not running too. No, I think something wrong there. So let's see. So let's see what it's currently considering. GB, Bluetooth. History. RG, GRGB, RB. One, two. Actually, they all look reasonable. But now my search space is a lot bigger, right? Because every level now it has 3 more moves to flip because it can always undo it. Then only will it detect that undoing it doesn't make any sense. So GR, GBR, BB, BBR, G. Equal to 0, not, that's why. Equal to 0. So let's just take every 1000 nodes. And the node. And here we can modify our printout, the length of node 1 and node 0. And so you can see the computational complexity here. The first up to 3, 4, we used relatively few nodes, right? We expanded up to level 4 with 28,000 nodes, but now level 5 is a lot more than that. It keeps going at level 5. This is not even code. we have 80,000 nodes. That should So here my local desktop is about 30% faster than I think, about 50% faster maybe. 97,000, 98,000. But still no solution found. So let me check. One problem could be that my check for the history doesn't drop anything. So let's check here. So I just want to make sure that's working correctly. So we have 100 nodes. Something should be dropped surely. No. Yeah. So the problem is this check here doesn't actually work. Now, surely some of them are reversed operators even at level 1, so I don't need to expand so many. And that should return the check. Oh, now it returns drop state. Oh, I haven't. Yeah, okay. So that's why this is dropped. So that seems to work. and we drop a state. GRGBBR. GRGBBR is in here already, so that's dropped correctly. So there's no problem with the check. Then it's simply a matter of having to expand enough resources. So we can run it for 1,000,000 nodes. Many different operators at level 5, of course. So let's, or maybe I make a scene. Okay. 1,000. B. Okay. 34,000. Something is still wrong here. If you check this shouldn't be possible, right? If we have pour 1 from tube 0 into 1, and then pour 1 from tube 1 into 0, that should be the same state. Pour 1 from 0 into 1. No, it's a different, it's not this fraction. No, it is. from 0 into 1 to 1 from 1 into 0. Surely that must be Oh, now I found a solution, 128,000. So, course 1 from tube 1 into 0. Tube 1 into 0. Then course 2 from 0 into 2. RG, yeah. Core 3 from tube 2 into 1. Core 3 from tube 0 into 1. Core 3 from tube 2. So that gives me RRG. So it gives me GGRR. Then 2 into 0. 1 into 0, which gives me core 1 from 2 into 0, which gives me BB, and then I bring over the R, and here's the solution. So our search algorithm works, in spite of the fact that it seems taking longer than I thought it would. So it's a non-trivial problem. That's always with exponential complexity and other kind of algorithms. You end up having to conquer exponential complexity here. But now we have a solution for the particular problem that we asked it to solve. Now I'm still a little bit confused about this one here where it has core 1 from tube 0 to tube 1. Core 1, tube 1 into 0. From 0 into 1. At the beginning, it doesn't seem to check if here that test seems to be not working. If I pour 2, pour 1 from 1 into 0, and then I pour 1 from 0 into 1, then surely I'm in the same state. It can't be any other explanation. So why didn't that not trigger that it would get dropped? Strange. Pour 1 ball from 1 into 0, then pour 1 ball from 0 into 1. See if that has something to do with our state. Yes, state.copy, then we copy it. No, these are just sounds. Okay, so the Google Collaboratory also another 10,000 they will find the solution. Presumably, what was it here? 128,000. 129,000. Okay, so now what's the maximum length of the path that I can actually generate with this in this particular puzzle, and how many different states actually are there? How would we answer those questions? So think about that and try and fix your code so that it can provide answers to those questions. And here's our solution in the Google Collaboratory. I'm still confused about this reversal. So let's analyze that a little bit. The problem was this code together with the search, but now I want to limit it to problem was 0 into 1 and then 1 into 0. So just to show you how to debug problems like that. We just generate this 0 into 1, 0 and 1. Call that the test function. And then we call test here. Maximum 1000. And also for the search. I print out every node here. Other than that, I don't want to. Here are our nodes. It's already up to level 4. So here's level 1. And over 1 from 0 into 1. Okay. Over 1 from 0 into 1. Over 1 from 1 into 0. So here it actually tells us this is the same, right? BG, BG, GR, BR. So we start out with this, and it doesn't match that. So somehow the initial state is not, because it's not in the history, that's why. The initial state should be in the history, otherwise I don't consider repeating it. So the initial state is here. And then the children of that is what we want to have. And no, wrong search. So let me fix it in here. Yeah, so there was a bug. I should check the initial state too, because I was already in that state when we started. And then let's run that. And now we should have probably significantly less nodes to expand. Now I'm already up to level 6, actually, at 33. So you see, like a small mistake in your nodes can lead to quite a big change in your search function. So we're running at 62,000. This is our state. Search again. Now here, these two are not really necessary. They're just debugging functions. 78,000. We went up to level 6 a lot faster, I thought. Like, here now I reached, I don't have the printout. Here we reached level 6 after generating 26,000 nodes, whereas before at 129,000 we were still at 5. So this is how. I should have expanded faster than that. So no, it's only 6 now because it counts the initial state. And I need to fix that part too. Here, yeah, it actually is not that much faster. But here I need to give it an action, so the action that I did here was just to add the initial state. Otherwise, the zip is not going to work afterwards. And then so it's not going to lead to that much speed up. So we need to give it an action here that we executed. So the action that we executed was the initial state. Is this okay? State is not good. I think it's the wrong. I think this is using the. Okay, now it's happening. Okay. So how many states should be in the puzzle? What's the maximum number of states you would expect in the Dr. Eureka puzzle? How can you figure that one out? Like right now we have 100,000 states that we search through, but that's because we're looking at the problem as a tree rather than a graph. So that means that if I have the three tubes, and currently in the tube I have basically one problem is if I have R, G, G, empty, B, B, R, right? Then I could do G, G, R, R, B, B, bring the red one from here into there, and then from here I could go G, G, R, R, B, B. This step. Or I can bring the R directly over in one move, in which case I will get G, G, R, R, B, B with an empty step. So those two are the same, right? They're equal, but they're we get to them through different paths, through different operators. And as I'm executing, nothing repeats here. I bring the red one from here to there, then I bring the red one from here to there. There's no repetition. All three states are different. So the tree search, so how many nodes did we actually save? 112. So we saved about 20,000 nodes now by taking the initial state into consideration when we're checking for repetition. So out of 120,000, that means we have like a 20% speed up by fixing a simple mistake like not adding the initial state into the states that we have visited. But there aren't actually that many different states in the puzzle, right? The only reason why we have 120,000 is because we're actually looking at it as a search problem, and every path to reach a particular state is considered different. Another problem where we end up in the same state but along different paths would be something like this. R, B, B, MT, R, G, G, right? From this state, I can either do pour 1, so I can do B, B, R, G, G, R, and then from here I can do B, B, R, R, G, G, right? Which gives me this state. Or I can take this red one first. So I can do R, B, B, R, G, G, and then from here I generate B, B, R, R, G, G. Right? And those two, as far as the search algorithm is concerned, would be different because we only check for repetition along this one trace through the tree, and here we don't repeat any states. But the fact is, the search space is actually a graph, so those two end up being the same. Now, if there is any other movements that I can make, then all of these can happen before we end up with those two states. And then, of course, from those two states, there may be a huge amount of work that I can do where I can still move things around without repeating themselves. And only at the end do I realize that there's no solution. Right? So then, instead of expanding it just once, I would have to expand it twice here and actually figure out that there's no solution. So, if we want to design, if we want to figure out how many states there should be or how many states there are, then we have to, first of all, we want to think a little bit, and then probably based on this analysis, we can improve our search algorithm. So if I have 6 balls, 2 red, 2 green, 2 blue, then how many ways are there in which I can arrange them? After, how many did I say? 112,000. After expanding. see about the colors. Okay. So if I have two red, two green, two blues, then one thing that I can generate is red, red, green. Let's make it the rainbow. Red, red, green, green, blue, blue. I'm also colorblind. Red, red, green, green, blue, blue would be one arrangement. But of course, I can also generate another one which is blue, red, green, blue, red, green, and any variation of those. So how many possible ways are there of arranging 6 balls? How many choices do I have for the first ball? If I just have 6 numbers from 1 to 6, 1, 2, 3, 4, 5, 6, how many ways are there of arranging 6 numbers? How many choices then do I have for the first number? 6, right? Then for the second number, 5. And then, which is 6 factorial, which is 720. So that's 720 different ways of arranging the number, right? Arranging 6 numbers. Now how about our balls? Correct, and why 2 factorial? Because I have 2 red ones, so here, whichever one I pick doesn't matter, right? This red one or this red one, I end up with the same thing. So that's only half 2 divided by 2. If there's multiple, if I have 3 red ones, then there's actually 6 possible ways, so it will be 3 factorial. So I have 2 red, 2 green, 2 blue. So that will be 720 then, divided by 2, multiplied by 2, multiplied by 2, which is 8, right? So 720 divided by 8 is 90. 9 times 8 is 720. 90. So really, there's only 90 different states, right? But we're doing a lot more work than 90 states. That's because this is not the puzzle, right? This is simply the arrangement of the balls. So now, we're not dealing with the tubes yet, right? So how do I deal with the tubes?
unique one. So,
Yes, the way I implemented my search right now, each tube is unique. Yes, so I cannot move the tubes around, swap the tubes. We can change the algorithm to allow swapping of two tubes as well.
the maximum number of the posts are 4.
I think I don't have any. I think it's 5. But so far I haven't put in any maximum for the tube. So I don't have any limits. So we also allow puzzles where we have a maximum number of 6. But the way that I would think about this is now I have my balls, right? And now I need to put in the markers for the tubes, right? And so this would mean B and R in the first tube, G, B, R in the second tube, G in the third tube, right? So then, how much does that add into my search space? No, not 8 factorial. I don't think so. Now, first of all, the positions that I can put it here, right? Or here, or here, or here, or here, or here, or here. So I have 1, 2, 3, 4, 5, 6, 7 positions for the first one, right? And then I have how many for the second one? 6, correct, because one of them is used already, right? And also 1, 2, or 2, 1, 2, or 1, 2 doesn't matter in which order. So as long as there's a marker there. So there's 2 different possibilities to arrange them. Right? So that should be 7 multiplied by 6 divided by 2 factorial. Right? Which is the same as, you can also, that's a formula for not composition, close. C, big C.
Yeah.
C, 6, 2. Right? Choose 2 from 6. Right? That's exactly that formula. So choose 2 from 6 is 21, right? There's 21 possible ways, so we should have 90 So total space that we have should be 90 times 21, right? Which is equal to 200, 2,100 minus 210. So should be 1,990. 1,890. How many is it? 100 times 21. 1890, right? Okay, but now I haven't done the flip yet, right? So for each one of those, I could specify that the tube can be upright or reversed. Right? So that means here I have this multiplied by, because I include all the flipping operations, right? So that would be multiplied by 2 times 2 times 2. So that multiplied by 8. And I think that's the correct answer. 2. Yeah. Yeah.
About the separator of the colors of the both, can they be the both of them at the right mode, right? So that there are two empty tubes.
That would be possible, yeah. But it wouldn't, yes, that I haven't, so that may be one more. Maybe some more here, that's true, because they could both be bang bang,
yes,
and then B, R, G, B, R, G. So then, if the maximum number in a tube are 5, then that wouldn't be possible, right? Because in that case, there must be at least, there must be at least 2 full tubes ever, always. At least 2 of the tubes must be full. Otherwise, this is not going to work. Because if I have 2 empty tubes, then 6 balls must be in the only full tube that is left. If I don't allow 6 balls, if I maximize it to 5 balls in a tube, then at least 2 tubes must be full. So then that wouldn't be a problem. That's not what I implemented in my search here, right? I allowed an unlimited number of tubes. So we can, an unlimited number of balls in the tube. So now, let's set the maximum to 5. So now modify the code so the maximum number of balls in the tube is actually 5. Then how would you modify your code? So that it matches the game. So now we don't allow 6 balls in a tube, or a maximum of 5. How can I do that? Actually, it's still wrong, because if I have 7 choose 2, then that's not correct here, because I could have BRG, empty centric tube, and then GBR.
yes,
right? So this part here is not quite correct. So there I have 7, and then I have another 7. but then I still have two, whether it's 1, 2 or 2, 1, doesn't matter. So it should be 49 divided by 2. So that would be 20. Yeah. And here, that wouldn't be allowed then anymore. So as a upper bound, it would be 49 divided, so it would be 24.5, 25. So the number of states would be less than this. In this case, there would be an upper estimate, an upper bound. But it's pretty tight. It only deals with the number of 6. So let's see what change happens, or what impact it has on our search space if we limit the number of balls to 5. And actually in the code, that is not too difficult to do. When I generate the children, here, how do I need to modify this code so that I will have a maximum of 5 balls in a tube at any point in time? And here, for example, it did consider 6 nodes in 6 balls in one state. So we don't want to allow that. Then all we have to check is, because we're moving balls, right? So they go into state 2. So I check that the length of state 2, which is how many balls I have in state 2 at the moment, plus the number of balls that I move into it, that has to be less than or equal to 5. So that will solve that. There nothing changes. And then here it will run our search algorithm now. And how do we deal with this problem here? Now we still have way too many states, right? We're expanding 100,000 because of some ways in which we can reach the same state using different movement operators. And it will consider all of them differently. Now, that's usually what we do in AI. That's not too bad, but if you wanted to avoid that, you basically need to implement what's called a taboo search, where you add an additional data structure, a dictionary, and you check if the state that you generate, not only is it in your list of, in your history, but you also make sure that it's not anywhere else in the search tree that you're searching through. So in this case, we would have to go through the queue and check if that same state already exists anywhere in my queue, not just in the history, right? And now it's faster, probably 78,000. So that, making sure that we cannot put 6 balls. The reason why 6 balls are problematic is because there's only all possible ways in which you can generate those 6 balls, and then you can take them apart. There's many operators that you can use. So the branching factor there, you can use 1, 2, 3, 4, 5, and 6 balls you can pour, right? So your branching factor there is 6. Then you can pour it into one tube or the other tube. So your branching factor is 12. So that's what blows up your search very quickly. Now let's check to make sure. And this is the check that we implement now. That depends very much on your particular search domain, whether taboo search, whether it's useful or not. Depends very much on if you, the structure of your search space. Basically, how often do the nodes actually repeat themselves? How close, how connected is your graph, basically, right? Now, for this puzzle, I actually don't think it's too bad. Some other puzzles have a much more graph structure-like. In particular, motion planning for humanoid robots is very, very much a graph instead of a tree. Doesn't have a good tree structure at all. The Dr. Eureka game is not too bad. So probably when you look at the runtime, the problem is that you add all the nodes into your queue, right? And then that means that the size of the queue, the amount of memory that you use, grows exponentially, right? Because if I have 12 successors, then at the root I have 1 node, but then I have 12 nodes at level 1, and at level 2, each one of those has 12 children, right? So that would be 12 squared, which is 144, and then it goes up to 12 to the power of n, which means that the queue actually, as we go through the levels, eats up a tremendous amount of memory, exponential amount of memory, which means that since you run out of memory a lot faster than you run out of runtime usually, we can have, even in Python now, you can see we generate about 1,000 nodes per second, right? So that means, because when you look at the screen print out, I print out every 1,000 nodes that, not that we generated, but that we actually looked at. So we're processing about 1,000 nodes per second. One node means a millisecond. So if I run the code for an hour, then I will have already used up 3 gigabytes, 3,000, more than 3 billion nodes that I've generated at that point. 3,600 multiplied by 1,000. No, sorry, 3.6 million nodes that we have generated. Then if I run it for 10 hours, it would be 3.6 gigabytes, like that much longer. So you run out of memory very, very quickly. If I now need to go through that queue and check if that node already exists anywhere in there, or if I've processed it, then that could be a huge amount of overhead, right? Every time I expand a node now will take a lot longer because I need to check thousands of nodes to see if they are already in my queue. And that can be quite slow if you actually have a problem with the tree structure where most of these checks will fail. But next class, we will look at motion planning in the grid world, and you'll see, I mean, it's easy to see that the grid world, it is actually essential to do that, because the grid world, you have some kind of environment, right? And then you start here, here's your initial state, here's your goal state, and there are some obstacles in the way, right? Now, if I consider, so then what would be the state if we're implementing this as a search? What do I think should be the state, or what should be the state representation?
The robot position.
It's just the position of the robot, right? So that means that could be my state, right? The current position. But the problem is that here, there is many, many different ways to go from here to there, right? I can go this way. 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 All of them will lead to that same state. So in that case, we do need to come up with a better search algorithm than just using the straightforward artificial intelligence search that we're doing in this case. Right? It will be a tremendous overhead if I don't check if I visited this position already before. And there's two factors to it. One, how much graph I actually have, like how many states actually repeat themselves, right? How much not tree-like is my search problem. For path planning for robots, we see it's very much a graph, much more so than a tree. And the other thing is, how easy is it to check if I visited this particular state before? Because some states are extremely difficult, or it may be a lot harder to compare states to see if they are equivalent or not, as far as my search is concerned. That's the other case. Somehow I need to have a good data structure so that I can easily check if this state was visited before or not. And the AI search is kind of usually, that test is not so cheap which is why we usually don't do that, why we usually assume a tree-like structure. But for the navigation problem in the grid world, it's very easy to check if the state is already in the, has been visited or not, because I can either just, the position is only two coordinates, x and y, right? So I just need to check, is x equal to this, is y equal to that, and then if it's true, then I visited this state. So it's trivial to compare the whether a state has been visited or not. So next week then we'll be looking at the Floyd-Warshall algorithm. Now the search, the AI search that we implemented so far is actually what's called a breadth first search, because we expand one level at a time, right? That works well if your solution is shallow, if there's not too many steps in the search path that you're going through. Right? If you can also do what's called a depth first search, which means, and that's the usual way that we introduce search in the artificial intelligence class, where you start at the root node, you expand one node, then you expand another child, you keep expanding the children. If you don't find a solution, then you backtrack. Only then do you backtrack. That search is sometimes, it is preferred, is actually what's implemented in real search algorithms. Yeah, depth first search is not what's implemented. A variation of it is what's actually implemented. But depth first search is advantageous if your solution has many different steps, but actually many different paths lead to the solution. Because then, let's say I need to go to level 20. If I do breadth first search, I'll never get there, because I'll eat up all the memory in the universe before I can expand up to level 20. Or 100. But if there's many different solutions, then I can keep going down to a deeper level very quickly using depth first search. If I don't find it, I try another version of that path, and there's a good chance that I find the solution there. And the big advantage of depth first search is that I only need to be able to do the backtrack here. So the memory requirement is only linear in the depth. So you do not run out of memory using depth first search. That's a huge advantage. So those are the two types of AI search algorithms that are usually used. And the big advantage of depth first search is that we use much less memory. It goes deep very quickly, but the problem is if your search space is regular, which means that all the solutions are at the same level, then depth first search will work just great. That's the algorithm to use. If you have a search bound, if you know, for Sudoku, for example, you know that all the solutions, if there's 10 empty cells in the Sudoku puzzle, you must add 10 numbers. There's no way that you can add 9 numbers and get a solution, right? You must add 10 numbers. It's also impossible to add 11 numbers because there's nothing you can fill out in anymore. So in that case, depth first search is your best solution, because the search space looks like this. Here are all the solutions. So you just search down to depth 10, and then you start expanding that until you only use a linear amount of memory, and it works very nicely. Depth first search is problematic if you have a problem like the Dr. Eureka, where we're not sure where the solution is. So maybe in one step I can actually reach the goal, but because I went the wrong move in the first step, then there may be an possibly enormously large, or in the worst case, infinite search space. If I can generate new structures or things like that, then I may have an infinite search space where my solution will just keep going forever. But it'll never actually check to see if there is any other way at level 1 or level 2. So practically, what we implement in practice for AI search is called iterative deepening, depth first search. And the idea is that you start out with a depth limit, because you must have a depth limit for depth first search to avoid it falling into an infinite subtree possibly. So iterative deepening works by having the tree, and then we start out with level 0, which basically means we just look at that node, we say, is it a solution? Because it may be that the initial state is already a solution, which means we're done, right? So we check that. Then, if we don't find a solution, then we increase. Then we say level 1. So now, I allow the depth first search to proceed up to level 1, which means it checks this one. It starts again from the root, checks this one, no, generates some children, but it's not allowed to go there. So it'll have to backtrack, try this one, backtrack, try this one. None of them are a solution. Then we allow up to level 2. So now it's allowed to expand up to level 2. So we keep increasing the depth limit that it's allowed to search to. Now, most students, when they read about that algorithm, they say, well, this is crazy because our problem is the algorithm takes too long, right? It's too slow. But now we actually do a lot more work, right? We expand this one first time. Then, for the next level, I expand this one plus this one. Then, for the next level, I expand those 3 plus these 9. Right? So I'm redoing a lot of work. But if here I have actually don't know what that value. The point is that most of the nodes for a particular search are always in the leaf, right? Because if I have a branching factor of b, then what I repeat is here, these ones are repeated, but that number of nodes is much less than the number in the leaf nodes. If I have a factor of 12, for example, then here, this is only 1/12, right? And this is only 1 over 144. So this is 1% of the nodes that are 2 levels up from where I'm currently dealing with. Right? So the extra overhead of doing the iterative part is usually minimal. It's like 5%. Even if your search factor is 2, branching factor, if your branching factor is 2, right? Then 50% of the nodes are in the leaf, and the sum, all of them in the tree summed up above you, are also just 50% of the node. So if your branching factor is 2, you have about a 50% overhead by using an iterative deepening approach. But you can run that algorithm for weeks because you won't run out of memory. You only need, if your search depth is 50, you need like 50 times some data structure, not 2 to the power of 50 times that data structure, right? So in that case, we really have no choice but to accept the fact that we need to use some kind of depth first approach. If your factor is 12, then it's on the order of like 1% extra runtime that you incur by doing the iterative deepening approach. So in practice, this is what we run. Iterative depth first search, which basically its behavior is exactly like breadth first search. And that's what you need to do for irregular search space. If it's a regular search space, then you can just set your depth. If you know that there's no solution less than 5 steps, then you can set your depth limit to 5 and just run it at that. Make it a little bit faster. And there's all kinds of variations then that you can deal with. But that's the standard way for attacking these kind of planning problems like the Dr. Eureka problem. In fact, in order to find out how many different states there are, I can simply run the planner and store them all. Now that I analyzed that it's only a couple of thousand of them, I can just store them in a dictionary to see if I've visited them before or not, and then check the length of this. That would work. And the maximum solution length, then how will we find out about that? That means I would have to take any 2 nodes, right? Calculate the shortest solution and then check which one of those is the longest one. If we do that, you actually end up with 7. If I remember correctly. Yeah, 7 moves in order to get from any state to any other state. You can also look at it by checking, running depth first search, how far can you run before you're guaranteed to repeat a state. And that will be twice that number would be not twice that number. You still would need to check what because that would tell you what the maximum number of steps is from that initial state. Then you would need to check what's the shortest distance from any state to this particular state. But we'll talk about that using the grid world example next week. And next week we will also have our first class with the German students. So make sure that you are here for that, and we'll probably just do the first class. First part of the lecture will be the class, and then we will call them at 3 o'clock. 3:15 there, our time is 8:15 in German. Okay, good. Any questions? Oh, no, no, Tony, can you take the laptop back to the main office? Yeah, this one. They want back. No, the main office.
Main office.
And I need to remix my recording.